Hey everybody, and welcome back to Calc 3 Online. So the plan for today is to talk about a very useful optimization technique called Lagrange Multipliers. And before you watch this video, I definitely want you to watch the video by Dr. I think it's Schreffer. And he has a really good one on like the geometry behind the geometric idea here, and it's really hard for me to do that in these videos because I don't have the ability to make his pretty graphs and all the stuff that he does. So make sure you watch this video before you watch this one. Basically the idea here is we're not going to be just so let's take think of this surface right here. You could do local max min optimization stuff, and you can find the highest and lowest values of this thing. Then if you constrained it on some sort of bounded domain set or something, then you can get an absolute max or min using extreme value theorem stuff that we've been talking about. But there's another version of optimization here, and that's when we could optimize a surface based on some sort of constraint. So we're actually going to do one here in a second. I think I just jumped 2 slides. So we're going to do this one here in a second where this could represent some sort of profit model, but you have a budgetary constraint for that. So, X and Y could this is very real world kind of idea here. X could be some sort of advertising cost, and then maybe this is production capabilities or something like that. And so you could have some sort of profit model, but you have to do it based on this sort of constraint function. And so here it's you've got a surface, and then the constraint function is right there. And so we're basically figuring out what's the highest and lowest value this thing attains, but on this curve, okay, this red curve, this constraint. The way it basically goes is there's tangent lines all along to these, both the function f and the constraint g, and there's a spot where the two tangent lines to some level surface of the function f and the constraint, there's a spot where the tangent lines will be parallel, or they're shared, I guess I should say. And at that spot, they're normal vectors, which is the gradient that we're talking about, right? Because we saw that with tangent planes, the gradient is very related to the tangent, or the normal vector, sorry. Those will go in basically the same direction, and so they're going to be parallel. And so this is a gradient for the function f, and this is a gradient for g. And that's what this equation basically says. And this is the formalism of Lagrange multipliers for a function of 3 inputs, but it scales perfectly to higher dimensions. So you can, and lower, so you can do f of x, y, this one that we're about to do is just a function of 2 inputs. And, you just drop z in this case. But basically there's the gist of what we're doing with Lagrange multipliers. The math is really a system of equations. We basically have a gradient of f this is a vector, right? So this vector has to equal a scalar. This right here is just a scalar, just a number, right? Of the gradient of g. Basically, that's our way to say that one vector is parallel to another. And we're sort of forcing that to happen. So we get that nice, we're basically at that spot where they're tangent. And then we also, this is the constraint function, and we're going to have that be some sort of level surface also. So And then we're basically going to solve a system of equations with these. And like, that's what I kind of have down here. So, you know, based on this part right here, you have these first three things. So we have like, you know, if we think about the components, we have the first component of f needs to equal lambda times the first component of g, second component of f equals lambda times second component of g, and so on for this one. And so then we have another equation. So when you solve Lagrange multiplier problems, if you have three inputs, you actually are solving a system of four equations. Maybe that's good to write down. So for three inputs, you are going to have a system of four equations in four unknowns. And then like lambda is one of the unknowns here. And then, you know, if you have two inputs, you basically would be solving a system of three equations. And so these problems can get pretty big because systems of equations definitely take a while to solve. So today I just want to do two examples. So let's get into it. All right. So this is my profit model function. And this is my constraint. It's like the budgetary constraint function. Very like real world kind of problem here. So, you know, one part of it is we said that the constraint function, we basically are going to, you know, have a system of equation. One of our equations in our system comes from that part right there. And so this is kind of like a weird thing to do. But basically I'm going to think of, so this is like G, okay, my like constraint, and I'm basically going to think of G actually as a function of X and Y. And so what I'm really doing is I'm taking like this and I'm like moving it over and I'm like basically setting G equal to 0. This is like a common trick that we do in these Lagrange multiplier problems. So I'm going to do this because what's going to happen, so in this case we would get that. What's going to happen is by doing this, I sort of pull the constraint function, which is in 2 dimensions here, up onto this 3-dimensional surface, right? So I've basically done like an algebra trick, honestly, where this is now like projected onto this, just like, you know, I could take this, you know, if this was a function in the plane, I could like project it up onto here if I just sort of, even, you know, just doing exactly what I did here. So making it like understood as a function of X and Y. So that is going to be nice because now I can take my gradient of G. And in this case, the gradient of G is just going to be 20 and then 4. Right? And I'll need a gradient of f. And so the gradient of f here is that. And then what we're basically doing in these problems, right, is we're setting this gradient of f equal to lambda gradient of g, right? And from that, we're going to be able to get 3 equations. And I'm also gonna, so the gradient G is a constant vector here, which is nice. So I can also just scale everything down because 20 and 4 are nice together. So I can just do this as 5 and 1, which means that like, you know, my system over here, my like first equation could just be 48 minus 2x minus 2y equals like 5 lambda. And then I could have 96 minus 2x minus 18y equals just lambda. Right? And then you basically are just trying to solve a system. What I would do is, you know, you've got this nice lambda solved for in the second equation. So I would take this and I'll just plug it in right there. And you'll get this. And from that, you know, this is just plugging in what lambda is. I'm just going to save you the annoying part of that. So you can simplify that down and you'll get x equals 54 minus 11y. Okay? And so now I'm going to use my my fourth equation, or my third equation. So I had, 1, 2 here, and then I have 1, 2, 3 variables. So I need another x and y, like I've gotten rid of lambda. I need another x and y equation, but that's my constraint one. So this is where I'm using this and this part. And so let's do blue. So using just 20x plus 4y equals 216, I plug in what x is, right? 20 times 54 minus 11y plus 4y equals 216. And then also going to save you the annoying algebra there. Simplify that down. You got y, you can get y equals 4. And then, you could just go ahead and like go back to this or something. And if you plug in y equals 4, you're going to get x equals 10, okay? And so the max profit, we now know, happens at these two, this x and y spot, right? And so now we can just go to my profit function and just plug everything in. So we can do f of 10 comma 4. And I'm also going to save you the annoying plugging and chugging there. If you just go and plug everything in, just up here, you basically get that the max profit is should be $540. So this is the idea. What we basically have done here is we've solved a system of 3 equations, and whenever you see 2 inputs, you know that you're going to need 3 equations. One of them always is the budget curve. Here it's just a line, but I guess a line is a curve with 0 curvature. So one's always going to be that, because we want it to, we're forcing it to be on this path somewhere. And then the other one is, based on this algebraic idea that we need the gradient of one function to be equal to a scalar of the gradient of the other. And the weird trick, I think, to me always was just that, like, in order to make this make sense, what we're doing is we're taking this and we're, sort of thinking of it in a higher dimension. Like, you can understand this as a line in 2D, but we could also like pull it out of the 2D plane, and we're thinking of it as a plane in 3D and looking at where it lines up with the gradient of this. So I'm going to do one more example, and we're going to do it right now. Oh yeah, and I thought I might need the 2 slides because I thought that problem was going to take longer, but I ended up skipping some of the annoying algebra, so we don't need to do that. All right, so this one, we've got so it's a little hard to tell, but this paraboloid here, it looks kind of circular, but because of the 2, right, it's going to be stretched differently. It's not like a circle, it's like an elliptic paraboloid up there. And so that's the thing I'm trying to optimize. And the constraint is I want to optimize it on the circle x squared plus y squared equals 1. So, because it's stretched a little bit, what happens when you take the circle and you pull it up is you get that, this kind of like, it's going to look kind of like a Pringle. You can kind of picture like I'm going to attempt to draw it this way. Let's see. Looks kind of like that, if you can imagine. But basically, this part is right here, this part's right here, and then it's going to go back there. And the reason it's not going to be, a perfect circle on this surface is because that surface isn't circular, it's elliptical. So you actually will get, something sort of interesting here. Because otherwise, if we optimized on a circle and it was circular, then it just literally would have the same answer all the way around. So what we should sort of expect here is you're basically going to get like 4 points where something interesting happens, right? So, this one is related to this minimum, this one is related to a maximum, this one is a min in the back, and then that one is also like a max. So we should get an answer where when we optimize on that constraint, we get some sort of like cyclic sort of answer, basically, as we go around the circle. All right. So let's just start by finding the gradient of f. Gradient of f is going to be 2x and then 4y. All right. And then I'm going to do the same kind of trick here. I'm going to think of this as a function of xy, which I'm just basically going to move the 1 over. So this is where I'm sort of imagining pulling this up into the higher dimension. And then take my gradient of g, and here I'll get 2x, 2y. Right? And then I need to make my gradient of f equal to a scalar of the gradient of g. And when I do that, I basically get the equations 2x needs to equal lambda 2y, and so it's like one of them. And then I also will get 4y equals lambda 2y. And I might as well simplify these. So I'm actually going to just take a 2 out of that one using magic. And I'm going to take a 2 out of this one, also using magic. This way I can just work with smaller numbers. Okay. Oh, wait. I just looked. I think this was supposed to be an x, and then this is supposed to be an x here. Yeah, we're good now. I think I just couldn't read. My x's and y's look very similar sometimes. Okay, that's good. So if you look at this first equation, there's basically 2 ways for this to be true. Either lambda can be 1, right, and then x equals x is like true, right? Or x could be 0, and then lambda can literally be anything, and you'll just get 0 equals 0, right? So you actually need to kind of think of this in cases. So case 1, we'll do the lambda equals 1 case. So if lambda equals 1, then that first equation is true, right? And we'll get 2y would equal y. And then you'll subtract like a y over, right? And then saying y equals 0, right? And then I'm going to use this, okay? And in that equation, so x squared plus y squared is 0 equals 1. And so in this case, x can be plus or minus 1. And then, and this is kind of checking out with what we know here, right? Because right now we're just sort of found one of the times that it happens is x equals plus or minus 1 and y equals 0, right? And then another case over here. So we could have, x equals 0, right? Could happen and make that first equation true. And then in this case, you can just jump to your g function over here, and we can work with that. So we have x is 0, so 0 squared plus y squared equals 1. So in this case, y equals plus or minus 1. And again, that checks out with what we kind of know here. And so then you can just go and evaluate at all those different points, right? And so you can do you can double check that this is true, but if you do f of 0, 1, it actually equals the f of 0, negative 1. So this is this point right here and the point back there. And in both of those cases, you'll get 2. And then if you do f of 1, 0, it equals the same as -1, f of -1, 0, and that is equal to 1. And so, I mean, you can go to like Math 3D and do this kind of thing. So this is, these are the max and min values that this function attains when projected basically onto here. And another kind of quick comment here. So we actually could do this problem by parameterizing this and doing a composition basically. And we could literally, I mean, we've done this with like vector valued functions. We've created this like Pringle shape before. And in this problem, that might actually be easier to do it that way. But the method of Lagrange multipliers is really useful if you can't easily parameterize the curve like this. So, here, this is like a teaching example, and it's really nice, and it works out well. But a lot of times you won't be able to just parameterize this red curve I got here. And when that doesn't work, the method of Lagrange multipliers is really the go-to. So you'll get to things where you don't just get nice circles and whatnot. And in that case, you just still do the same stuff. You'll find the gradient of one, gradient of the other, set them equal, get some equations, and then somewhere, whatever this might be, you'll just use that to basically solve the system. And so that's kind of an important note, because really here, you literally could just find the curve with a vector valued function kind of that we've done before, and then just maximize and minimize that. But that is not always easy. Actually, quite often, parameterizing a function or curve is really hard. And that's where this thing comes in handy.